Hi, welcome to the Signal Path. In this episode, we have another repair for you guys, and this is a Tektronix RSA 6114A. And this is a pretty capable unit. It's a real-time spectrum analyzer from 9 kilohertz to 14 gigahertz, and this particular unit happens to be fully populated, so it has all the options available to it. And those options are actually really expensive, so this one can do full 110 megahertz analysis window all the way from 9 kilohertz to 14 gigahertz. It has all the different digital demodulation software protocols. It has IF outputs from the back of the unit. It has all the features to be able to do deep memory, and there's a whole bunch of other capabilities. It has all of those, except for the fact that, well, it's broken. It doesn't work. Now, I promised that since the Patreon started that I would do more expensive repairs and more advanced repairs. Even though I haven't actually got any money from Patreon to buy equipment, I bought this in advance. I'm gonna have to make like 6 episodes to cover the cost of this unit alone. But if you can fix it, and if it's fixable, it would be quite a nice unit to have, and then it would allow us to do many more experiments as a result of having it in the lab, because I don't have anything in the lab that can do real-time spectrum analysis above 6 gigahertz, so this one should be able to do that. Now, this has a problem, and I'll show you what the problem is. This is a really big unit. It's quite deep. You can't see most of it from this angle. You can see my reflection on the screen. So, and it's also really dirty. Somebody has written with markers all over it. I don't know why someone would do that, but anyway, we're going to clean it up later if we can fix it. Or it may not be fixable, but it's quite an interesting learning experience. So I've already plugged it in. Let's turn it on and see what happens. There it is, and it's quite loud because it has many fans. And there you go, it's going to start to boot up. So it boots up and everything, so it doesn't have a silly problem of power supply failure or something. It has a difficult problem to solve. So you can see it has an Intel processor, and it's got clearly a motherboard in it, and it runs Windows XP Professional here. So it's going to boot into that. I won't waste your time because it's just going to go through the boot sequence. Once it boots, I'm going to show you what happens. And here we are after booting, and this is what you see. I've already connected the mouse to it. So you can see that it goes through an initial diagnostic, a power on self-test, a post, and then it fails the first LO, and then it also fails the signal path, which I take offense to. And so there's 2 failures. Now, the first failure of the first LO is obviously a local oscillator failure. It could mean anything. It could be a reference problem. It could be the main LO generation board problem. A whole bunch of different things can cause this. Now, the fact that the signal path fails, it's troublesome, but I wouldn't worry too much about it yet, because sometimes the LO generation is going to generate multiple errors, because the LO might be responsible for creating a whole bunch of other types of signals, in which case are going to be missing, and so the signal path will then have a failure as a result of that. So now if I go under diagnostic failure information there, and I look over here, you can see that the YIG loop error exceeded positive or negative threshold, so that's not good. YIG loop unlocked, so that's the YIG oscillator main LO generation is locked, makes sense. Offset loop is locked, interesting. Course loop is unlocked, so that's a fail there. The power supplies seem okay, 15 volts is 14.7, 8 is 7.6, they're a little bit on the low side, the 20 is too high. And also it says the first LO failed. And then under the signal path, you can see that these all pass, and then here it says signal power less than minus 55 dBm for the CW cal source. Now the CW calibration source failure could be related to the LO, because the CW source is most likely generated as a byproduct of the LO generation itself. So it makes sense that this would fail if the LO generation has failed. So this is the part we're going to focus on first as a result of that. And it also has a full diagnostic. You can run all of this. There's no point because we already have something to start with. So as I said, and if I go and exit diagnostics here, you'll see what happens. So it's happy to show you a spectrum, but obviously it's going to be wrong. Oh, it's taking its sweet time. Come on, you can do it. So it's under free run. Oh, there we go. Something's happening. Oh no, there we go. That's the Windows. Okay, if I go at the bottom, I can get the start menu up. It's clicking a whole bunch of relays. This must be coming out of the post. There it is. So, oh, there you go. So now it gives me this. It says hardware LO unlock, hardware failure, run tools diagnostic, but it still runs because Everything else is working. The digital section is working. So right now it's doing 40 megahertz span real-time analysis, sent to that 1.5 gigahertz at the bottom here, but obviously it's wrong. So it's not actually the correct frequency anyway. So there's not much else we can do from the software point of view. We have a place to look at, which is the LO failure. So let's go take the top and the bottom covers of this thing off and take a look and see what's inside of it and see what we can learn from that. And actually there's one other thing I should point out, is that I will show you this. I will show you the service manual. Yes, I forgot to mention that. So the service manual for this has basically no information at all. All the information it has is trivial things like software failures or some minor hardware failure so you can diagnose it. But if it, for example, it says you have a LO failure, well, send it to Tektronix. You have this failure, send it to Tektronix. You have everything that's failed, it's basically returned to manufacturer for repair. There's no schematic, there's a very coarse and crude block diagram, and I'll show you the block diagram so we can get some insight on the architecture of the unit actually before we open it. But I know I don't blame Tektronix for this, and the reason is because most of the companies, and this includes Keysight, this is not just Tektronix, this is everybody, nobody does component level diagnostic and replacement anymore, because the components are so, the modules are now so cheap that they just replace the module. So they say, okay, send this back to us, we'll put a new module in there, let's say a new LO module in there, we'll calibrate and send it back to you. No one's going to fix it at the component level. Here, the signal path, we're going to try to fix it at the component level, but that's about it, and interestingly, it just stopped. Let me turn it off. So this is the main concern with the service manual. There's not much I can do, but I'll show you anyway so we can get an idea of what's inside of it. But from then, we see what we can do. So let's take a quick look at the only block diagram that's actually included in the service manual to give us a quick idea of what's in there before we take it apart. Now obviously there's not a lot of detail here, but it gives us a generic idea here. So this is based on a Pentium processor, so you can see that there is some PIC MG processor board with a Pentium M on it, and that connects to the hard drives and so on, so there's a PC portion here obviously. Then we have this digital interface board, which is a huge motherboard inside the unit, which is like a glue platform that connects every periphery, every module, every component together and interfaces everything with ultimately to the PC. And all the GPIB, LAN keyboard, and all the other interfaces also come here. Power supplies come in and go, references, triggers, everything is handled there. And in acquisition memory for the real-time spectrum analyzer also seems to be placed there. Now this interface board has a whole bunch of slots, and these slots are for options to be installed. And as I mentioned before, this instrument has quite a bit of those options already installed there, which is quite nice. And you can see that the display adapter, touch panel, and all that stuff is also connected there. So there's an acquisition board, an RTIQ output board. These are real-time IQ generation for the real-time spectrum analyzer. You can see IF out and IQ out are additional options that could be there, and this unit actually has that, which is quite awesome. And then the data for those, which are analog, are going to come from the RF signal path, which has multiple modules in it. So they're going to treat this entire RF signal path as one platform with a whole bunch of modules in it. So they don't even tell you how these modules are actually connected to each other. They just tell you what is there. And this is very, very limited information, but it's still pretty handy for us despite the fact that there's so little detail in it. So the RF input goes into the RF signal path directly. And there we expect to find things like RF switches, preamplifiers, RF attenuators, which are normal things. And then there's a first converter, second converter, and a third IF module. And this is also typical if you've looked at some of my other repairs and some of my other teardowns and explanations of various spectrum analyzers. Multiple level converters is quite normal. And this is what you would expect to find. Now, a lot of times, one of the converter modules only works within a certain band of the frequency of operation. That's also to be expected, because often the first converter and second converter work in conjunction across different bands to bring the IF signal within a constant third IF module frequency band, and that then converts to finally signal back to the digital portion. And there is a first LO module, and this is where we would like to focus our attention first, because this is the error where the generation circuitry doesn't work and LO has problems and so on. So it's most likely here. It could also be in the reference oscillator module, because the reference oscillator module feeds signals into the LO module, but I don't get an error on this, so I'm not hopeful that it is in here. Maybe there is, and it's just something that's not detected. And then there is a 14 gigahertz extension, 4 gigahertz IF module, or the 20 gigahertz IF module. And this all depends on which model you have. So we're going to have the 14 gigahertz extension in there, obviously. And then the 4 gigahertz IF module is the core, the main one, where all of the units with the two different versions are going to be equipped with. So it looks all pretty nice and neat. And again, like I said, there's nothing incredibly complicated on this block diagram, very generic block diagram of a real-time spectrum analyzer. So now we can go and take the unit off and the cover off and take a look at what's inside it. It should look pretty interesting. All right, here we go. I think I've taken all the screws off. And ta-da! Look at that. There is a lot of stuff there. And as I mentioned, it is a pretty big instrument. So you're looking at the bottom of it. The screen is up there, and these are where the legs are, which you can put the instrument on kind of vertically on the ground like this. So we're looking at the bottom side, and this is clearly where the RF signal path portion of it is, and all the microwave components are clearly here. So we can follow the signal path, no pun intended, and we can see that this is the input. So you can't see the type N connector, but the type N connector is actually coming from there. And it goes into this first module, which is a relay, a microwave relay. And the microwave relay can either be fed from the front panel or from this cable. And following this cable over here, I can follow it and see that it goes to this norm SRC, which is a normalization source, I assume. So it's clear that they're switching this in and out in order to do some calibration perhaps, or in order to do some alignment. And you can hear the unit click back and forth in this trying to align. And this might be the cause of what that missing CW source is. Perhaps it's missing this alignment source, but that signal is almost certainly derived from the LO source and the synthesizer. So if that's not working, then this is not going to be working. So forget about that. We can't count on this for now. So then the signal, if you follow that, you'll see that the output of that is taken into an Aeroflex mechanical attenuator. Again, the first thing it sees is this mechanical attenuator after the switch, and that's normal. This is a 0 to 75 dB, 5 dB step attenuator. It's rated up to 18 gigahertz, so it has a higher frequency bandwidth rated than what the spectrum analyzer can do. And then it goes into this guy, which is a solid state switch, microwave solid state switch. The common is here. It has RF1 and RF2 as its outputs. So you either route the signal in this way or you route it this way. And this now begins to make more sense, because it's clear that for a certain frequency range, we're going to be sending a signal into this module, and for some other frequency range, we're going to be sending it in there, which seems to be going behind this whole platform where you can't see anything. And then it comes back out and goes into something else. So it's clear that this is this first converter, and it will only be on and only be functioning during the frequency range where it's appropriate. And I don't know what those frequency ranges are, because I don't think they're mentioned. Anyway, so if you continue down, we can find the second converter over here, we can find the IF module over here, and a bunch of other things are on this board. But if you look at the construction, it's clearly made of different modules, and these are all custom. None of them seem to be something that you can buy off the shelf. Some of these are actually made by Tektronix's internal production team that makes these modules separately, perhaps used for other instruments and other lines. I don't know if they sell them separately or not, but the board down here seems to be the control board, because it has all the ribbon cables connected to the different portions. Now, as luck may have it, as you can see, there is no reference board and there is no LO board here. So, of course, the LO board and the reference board is on the other side of this entire chassis. And by that I don't mean on the other side of the instrument, because on the other side of the instrument is all the digital boards. There are many, many digital boards, and the motherboard in there is nothing RF related to it on the other side. And I'll show you the other side later. And this cable over here is the cable that goes over there, and then it goes into the unit at the top, goes to the other side. So it looks to me, if I'm not mistaken, by disconnecting a few cables, the input and the cables, the IF cables that go through this to the other side to connect to the acquisition board, by disconnecting those, I should be able to take this entire module out as a whole, and then see what's on the other side of it, and hopefully we can find the gig oscillator and the LO generations board there. What I am worried about is then how do I power it back on while trying to debug it? Because at Tech, if there's a problem, they'll take it, they put a new module in, they close it back up. But I can't do that because I'm trying to do component level diagnosis. So it's going to be quite difficult, and I hope I can find a way to do this somehow. I'm not sure if it's even possible, but anyway, so we have to take this off. But now we have a generic idea here, looking at the first and second converter. And if you look here, there's a 14 gigahertz label written here, which means that this is most likely an up converter, perhaps, and up converts into the band of the second converter, second converter down converts back onto the IF, and the IF then goes back down again into the frequency band of the digitizers. So all that looks nice, and it looks like I have to also disconnect the fans here, and we'll see what happens from there. Oh, by the way, I noticed that these are disconnected. These two are supposed to go here, I think, and these are the external reference out and external reference in. That is a bad sign anyway, because it means that something has been done on this. But oh well, let's see what happens when I take it out, and I hope that this is not a sign of what if the board is missing completely, although I do see some connections here. So let's go and take it apart and see what we get. Should be pretty exciting. And here's the module. I managed to get it out, and I only had to connect a couple of cables here, disconnect I mean, and these cables are the cables that go to the IF board on this side, so they're pretty straightforward to disconnect. And at the back now, you can see two additional modules, and luckily those additional modules are there, and they're connected with the ribbon cable to the other side. So the other side of this board is what we were just looking at, and it's on this little towel here because there is nothing to rest on it, so I didn't want to squish all the cables. And I'm grounded, of course, because at this point this is floating and it's quite dangerous. We can damage it. So now I started taking a couple of the screws off, but I thought, hey, I'll show you before I do that. And now I don't see any Yig oscillator, which is a little bit concerning, but it could be a very small one somewhere in there. Now this is the synthesizer board. At least the reference synthesizer board seems to be this one, if I am not mistaken. And then this is the LO generation board. So this is a board that is suspect. This is what we want to look at. Luckily, it only has two outputs. It has one output here and one output here. And this output there goes somewhere which is labeled 400 megahertz. So it must be a subdivision of the signal for some of the other purposes, perhaps to the IF board. And then there is one over here which seems to be going, I'll show you on the other side, it goes into one of the converters. So it makes sense that this would be, some output of the higher frequency output, especially considering that they're using a rigid and high quality coax there. So let's go ahead and start taking screws off, and eventually this should come out, and then we can take it apart even further. Hopefully we'll find a Yig oscillator. It's really narrow, so the Yig must be tiny. I'm a bit concerned that I don't see it. I don't see anywhere it could have been that it's gone, but anyway, let's take it a step further. I assume that it's in there. I've been spending a lot of time with this guy, trying to get all these little screws out. And this is interesting. I just picked this up from Amazon because sometimes, these modules have so many screws on them. So I thought maybe I'll start using this guy to open them. And the reason I like this one is because it spins pretty slowly. And because it spins slowly, you can kind of roughly guide it a bit more easily. With a high-speed one, you can damage the screws. So it's okay. I mean, it also has this extender to reach the places. Not bad. No advertising for it. I just thought it looks cool. Alright, let's take a look at what's going on here. I've disconnected all the cables, and obviously this is going to come off quite nicely. And ta-da! Take a look at that. And on the other side of this is a machine piece, and you can see that there are RF absorbers on that side, likely over the parts of the circuit that have the highest frequencies, and again cause problems radiating back and forth between the surface of this and the board. This is very common. I've shown and talked about this before. Now if you look at here, we can see finally our Yig oscillator, and you can see it right there in the middle. Interestingly enough, this is a Teledyne part, and I hadn't seen the Teledyne Yig oscillator for quite some time. And this one, you can see they basically literally cut a hole through the PCB and put it directly there in contact with the bottom chassis there for heat sinking purposes. And then the output of it is taken with a micro coax and put on the board. So this part of the circuit is really straightforward. These are the two outputs. This is a 400 megahertz output, the top one. This one is a 400 megahertz output, and I'll talk about it in just a second. But this one is an output of the main LO output of the system. And it's no surprise that it's coming from it's basically the output of the Yig oscillator goes to a Wilkinson divider, and the Wilkinson divider has two outputs, one of which goes into this coax and then eventually to this BNC connector on the right. There it is, you can see. Interesting that they've lifted this off the board, maybe because of proximity to this line or some other purpose, I'm not sure, but it's interesting to see that. And then it goes out over here, and then if I follow this, I have the two paths now. Now this is nice because It means that this coax is basically a direct output of the yig. So I can directly look at this and see what is coming out of the yig oscillator. One of the common failure mechanisms of yigs is aging and diminished output power. And then that will not be able to lock the PLL loop, or perhaps not be able to provide sufficient power to the next microwave module. So that's one of the things we can check, which is pretty nice. And these are quite sensitive, by the way, not just to electrostatic, but also to mechanical shock. So there's some filtering, some amplification perhaps here, but it's neat to see the signal after it's split over here, going through all these various blocks, then goes into here, and this is a Hittite frequency divider. I think this is divided by 8. So going from that, this means that once this is divided by 8, and you can actually clearly see the signal path again, divided by 8, and the output is taken, it goes right through the board to the other side, and you can see 4 little vias there to create a nice vertical coaxial behavior through the PCB, and goes to the other side and then is processed on the other side, probably the rest of the PLL circuitry. But this is much more complicated than just a simple PLL for the yig. There's a lot more stuff here. And then it continues on going through a mysterious component, perhaps dividing it by 4 maybe, dividing it into 4 outputs, I mean. And then there's some more amplification, some biasing circuitry here, and there are filters in between everything and the biasing of the yig oscillator. So these lines that you see here are the lines that all go through this filter in between 2 of the cavities, directly going to the yig oscillator, providing a clean bias. Remember, any noise you pick up here is directly on the PLL, so you're screwed. There's nothing you can do about it at that point. So you have to keep this clean. And over here is interesting also, the 400 megahertz output. This seems to be a SAW oscillator. There is some PLL circuitry over here. Actually, if I'm not mistaken, this is a PLL core block. And then so you can see that there's definitely some loops again going on over here for that purpose. This is a phase frequency detector over here. A bunch of other logic. There's a lot of little corrections on this board. A lot of really neat actually connections. I will zoom in to show you. And then yeah, then on this side I have another, seems like I have another SAW oscillator. This is an 8-bit counter. This is a phase detector by Mini Circuits, and this, I'm not sure what this is. It could be another oscillator, maybe a reference of some kind, maybe a 100 megahertz oscillator. Some mixers over here, so it's clear that they're again using some stable reference to generate this other necessary signals, and then this phase detector is obviously part of a PLL, this counter perhaps part of a fractional PLL, and then they're closing the loop in there somehow. Now there must be a ton of stuff on the other side of this board, because I see no digital handling interface stuff. That must be all on the other side. And what else did I want to talk about? Oh yes, there's a bunch more dividers there. Over here, some more Hittite dividers. Whoever's at Tech designed this, they love a Hittite. Now there's analog devices, but they love that, because if you remember when I did the MDO teardown, the MDO C series, the 4000C, it had tons and tons of Hittite parts on it as well. So now these dividers are all gas, and I think if memory corrects, I think I've talked about that before, but anyway, I've made so many videos now I can't remember. So in order to see the other side of this board, I'm gonna have to take off some more screws. Uh-oh, look at that. My electrostatic was working in wireless mode. Ay, ay, ay. There we go. I disconnected, I forgot to connect it back. So let's go over here, and we can disconnect these. You can take these screws off and actually be able to look at the other side. Now, I don't think I can actually take this off completely, because I probably have to take this out too. Yeah, because this coax wouldn't allow me to remove the board anyway, because this is connected directly to the yig oscillator. Anyway, I don't want to waste your time you watching me take screws out. That's not very exciting. So let me take it apart a little bit further, and then we can see what's going on the other side of the board. Alright, one other step into the disassembly. This time I'm not going to forget to connect my anti-static strap there. So I've taken the yig oscillator out. As I said, this is a Teledyne part. There is absolutely no information that I could find about this. Must have been custom made for Tech. Although I did find some information about Teledyne yig oscillators in about the same dimension, and they range in frequencies from several gigahertz all the way to 13 gigahertz. Now I don't know how high the frequency of this one is, but given the architecture and so on, it's probably within a few gigahertz. Now I'm gonna not do anything to this. I'm not gonna take this apart yet unless it is broken. And you can see that it's obviously warranty void, and it's very, very sensitive. And it also has beryllium oxide in it, and you have to be very careful about these things. This one has a label. Sometimes curiosity can be a bit dangerous, so don't eat it. So having said that, you can see I've taken everything off. Now we should be able to flip this board And look at that, there's so many thermal pads on the other side of this pressing against components on the other side of the board. Now we were partially, and this is by the way the pad where the YIG sits, so you can see the thermal dissipation through there. Now we were probably expecting this because if I look on this side, there were no voltage regulators on this side and there were no drivers for the YIG, and there would have to be on the other side, so it's no surprise to find those thermal pads there. So let's put that aside. All right, and look at this one. Check it out. Obviously all of our power supply stuff is on this side. On the other side of this where all the other RF parts where there's nothing, and it's just a bunch of grounding and these pads either for the purpose of density regulation or for isolation or so whatever reason they're there. But you can see some of the extra, where was the part? There it is. This is where the output of the divider, the Hittite divider after the YIG comes, and you can see it comes over here and then it goes into some other circuitry. So clearly the loop is closed underneath and coming back on the other side of the board. These are the driver portions that drive the YIG. Whole bunch of transistors here for similar purposes there. There's a Xilinx part here, an FPGA or CPLD of some kind. So this is the digital glue, the digital core of this whole system is here. And what else is interesting on here that I wanted to show you? There was one other part. There was a 24-bit counter that I just found. I forget where it is now. I think one of these must have been a 24-bit counter. So there are more counters on here for the purpose of these fractional type dividers and providing the correct steps. But everything else is just a whole bunch of a lot of CMOS switches, regulators, a lot of capacitors, filtering and so on. So really straightforward. Now, as I said, because of the way that other board was made, I think I can put this all back together and have this board sit outside of the unit. And that will then allow me to power it on and touch it with probes and see what we can find on it and check the power supplies and so on as the very first thing we check. But I have to put it at least in here because I'm a little bit worried that this would overheat without any of the thermal pads connected to these regulators, because I'm not sure what the total power consumption of this thing actually is, but I suspect given that they've gone through the trouble of doing that, this might be. So this is probably an easy starting point. If I can get this thing to go back to the way it was. Okay, I'm sure I can do this. Anyway, I'll figure it out and then I'll put this thing back in there. There it is. And once it's in there, I can put the YIG back on and we can look at the output of the YIG oscillator because it is coming from the Wilkinson. We can easily look at that, and if that's not there, then at least we have a problem. We have a cause, and that's the YIG failure. But then I don't know where I'm going to get one of these. And there is actually ways to fix this. And people do open them and wire bond them and replace either the yttrium core there or perhaps one of the CMOS, probably most likely not CMOS, but one of the other driver ICs there, maybe gas drivers or something in there, and they try to replace it. But I don't have a wire bonding machine in my lab, so that's not going to be possible. And even if I did, I'd have to get a die version of the missing components. So I'm sure we can figure something out once we find out what's going on with it. But first thing is to measure it, and maybe I will jerry-rig some kind of a fan to blow over this as I'm doing the measurement. But anyway, I'm not sure. By the way, there's one feedback that I wanted to ask from you guys. My repair videos are very different from my reviews because this is kind of live. It's really ad hoc. I share what is on my mind, my mistakes and everything there. But for the reviews, obviously it's much more organized and structured because I'm presenting something that should be very well and very clean and very clear. So if you don't like this style difference, then I can just cut these down and only talk about once I know something. Or if you like the mistakes and kind of hopping around and goofing around a little bit, let me know and then I can keep it the way it is. So let's move on. Alright, and here is our first diagnostic setup. So I managed to actually put the board directly on the table, connect it up, and it's nicely accessible now. Of course I can only do this with this board, and I could not have done it with the other synthesizer board that's on the other side. I can only do it with this LO board. So hopefully the problem is on this one. Even though I have no schematic or anything here, it might be quite difficult to figure out what's going on with it. But nonetheless, what I'm doing here is that I am taking the 400 megahertz output exactly as it was, and I'm connecting it back to the same cable that it was connected to when it was inside the unit. The other side, I'm taking through a splitter, and this is a 90-degree hybrid. It doesn't matter, it's a 90-degree hybrid. I just didn't have a regular 180-degree one. So this is a 2 3dB splitter. So one of the 3dB outputs goes into the white cable, and the white cable goes back onto where that would normally be fed to. I didn't use the other cable because it goes behind the unit. There's no access, so I'm directly going into this using that. So this way the This is still in circuit except for the 3 dB extra attenuation here, plus a little bit more than 3 dB, but at least this will feed the signal back in, so we should be able to replicate the original errors and not have any additional errors because something else is missing. So this is kind of putting it back in the circuit, and the other side of the 3 dB splitted output I am taking to the Keysight EXA, and that will allow me to look at it, you know, from DC to 26.5 gigahertz. Like I said, most likely it's in a couple of gigahertz. This Narda splitter down here anyway is rated between 4 to 8 gigahertz, and if it's outside of that, it won't do a very good job at splitting 0 to 90, but it will still split the signal reasonably well. So now we can go ahead and turn it on. One other addition is that I put a little fan here to blow some air over it, and that fan is fed all the way over there with one of my power supplies. Nothing fancy going on, so we should be able to turn the fan on, turn the main unit on, and then see if we can capture any tones on the spectrum analyzer. So let's go ahead and try that. Alright, first fan on. Here's our fan, and the unit on. There we go. Right, but no smokes. Ah, but look at that. Look at that. You see, there's stuff there. Let's go take a closer look at it. Alright, so the instrument is actually still booting up, and so this actually, you know, this puts my first theory out the door, because the signal that I'm seeing here coming from the EEG oscillator, this is the second and third harmonic, the main signal coming out here, if I do a peak search on that, its power is 0.64 dBm, and this is after the splitting and then the loss of the cable, which means that the EEG oscillator is putting out at least over 3 dBm. So, and you can see it just moved actually a little bit as the instrument is booting. So indeed the EEG is okay, and it is producing a good signal. You can see it's jumping around again. So as the instrument is clicking around doing self-test, I'm assuming it's going to fail the post again. It's actually doing power on self-test right now, and I wonder if it's going to generate the same failure signal again. I'm sure it will, but clearly there is a signal present out of the EEG oscillator, so the EEG is not broken. It's indeed generating the right tone. And what was the frequency again? It's at 5.7 gigahertz, exactly like I thought, somewhere, you know, between 4 to 8. So that is nice, which means the Narda power splitter is working at the correct frequency range. So I'm pretty happy with that. Now we can take it a step further and see what else we can find. And the unit has booted again, and let me just show you, just so that we can be on the same page here. It is generating the same errors. You see this, the same failure here, the same failure here. So we have replicated the failure of the instrument exactly as if this unit was still inside the instrument. So that works out quite nicely. Now we need to find out, sorry about the camera movement here, we need to do some more debugging to see if we can find out any other cause of failure here. So now that we know this, we can zoom into the spectrum a little bit more and take a closer look and see if that EEG oscillator is locked or not. We should be able to tell by its phase noise. So now that we've done a peak search here, we can do this. We go under the span, we reduce the span, and take a closer look at it. Ah, look at that, interesting. Let's do another peak search. Do that again. What is our span? 50 megahertz? Ooh, that is not a good thing. Let's reduce the resolution band a little bit. Yeah, this EEG is most likely not locked. Now what I can do is let me increase the span a bit, because the way this instrument boots up. Let me take it out of the self-test. Let me exit the diagnostic here. There we go. I just took it out of the self-test. Now this is surely gonna. Oh, look at that! It changed. Interesting. Some interesting behavior. Oh, it's moving again. Ah, it's moving all over the place. Oh, and it's gone. Let me increase the span again until I find it. Where did it go? Ah, there it is. There it is, and no, the instrument hasn't come back yet. It's still clicking away. There it is, and it's centered again. I hope this is not utterly boring for you guys, but I have to. Okay, so now the instrument is doing a regular sweep. It gave me the same error. Hardware LO is unlocked. So now it's running, but the center frequency of the instrument right now is set to 1.5 gigahertz. So now this shouldn't move, because the instrument, the Tektronix one, is actually not sweeping across frequency. It's sitting at a fixed frequency. This is a nice thing because we can trace this. Peak search again. Go there. Reduce the span. Once again. Ah, there you go. I already see it. I already see it. This is not a locked system. But it's actually not that bad. It means that the course frequency is actually correct. So the coarse frequency is working, the fine loop is not working. And I believe that was consistent with the errors, but this is clearly an unlocked gig oscillator. We can see by how jittery it is. It's moving around, and I bet you if I put my finger on it, I'm just going to take my finger and I'm going to gently press on top of the gig, okay? And I am almost sure that I would be able to affect the frequency. Let's try that. I'm going to try that right now. I'm going to ground myself. You see? Look at that. Isn't that great when a prediction comes through? There it is. I can in fact do FM modulation if I'm fast enough. So yeah, so it's definitely not locked. So that's a great place. Now we have an idea. Let's go ahead and see what the first thing this gig is actually connected to, and we're going to trace it out and figure out our way forward. Let's take a closer look here. First of all, a couple of things I wanted to point out to you. Look at these little fixes they've done. Look at that, so neat, so clean. Obviously this board has had quite a few little mistakes in it, and they have fixed them up because they probably didn't want to spin the board, and they managed to get it to work. So that's kind of interesting to see. But looking at this section here where the signal distribution takes place, we can see that from the Wilkinson we're going through a bunch of passives. I doubt that they are dead here, but we can still check. And if I'm not mistaken, going over here, this path, and we're going into this device here, and that device is, there's the part number of that thing. That's an HMC 363, and I believe I mentioned that was a divide by 8. So I want to check to see if the signal is getting into here, and if it is getting into here, is it coming out divided by 8 or not? Because if it's not making it here, then something is broken here. It means that's just the gig just simply not closing this loop here. That would be a problem right off the bat. And then the other problem is that is it coming out? Is this actually doing division? So let's take out the datasheet for this just to make sure we understand the pinout, although it's pretty obvious from looking at it over here, and then we can measure it. Now how am I going to measure it? Well, we can measure it with an active probe. That's not a problem. We can measure it using a spectrum analyzer, but I don't want to disconnect my signal here from the spectrum analyzer. I want to have that. And I think since I have the S-series oscilloscope, and since I have a CAT scan, we should be able to do this. And I'm going to try to use the Keysight S-series scope. This guy has 8 gigahertz of bandwidth. It's easily enough to be able to look at that signal with an active probe, and I have both of those things. So let's give it a try. So while the scope is booting there, let me show you the probe. I've shown you this probe before, and this guy is not happy that I took his spot. What are you doing? Anyway, so let's take a look. I'm going to use this active probe, and I've shown this before to you. You've seen this before. It's nothing out of the ordinary. It's the 7 gigahertz active probe there. But what is nice is that I have this attachment, and this attachment allows me to use these extremely sharp pins whose distance I can adjust like that and do a differential probe directly on the PCB. These are very, very sharp, and they are springy, so they make a nice contact, and I can press down and monitor the signal. So this is a very nice and easy way to do this, and this is a very high, 50 kilo ohm or something. I can't quite remember what the impedance is, but it's quite high, so it will have minimal loading effect on the circuit, and this can take DC, it can take all that, so it's quite safe to use. Let's hook this up and measure this to use this to figure out if the signal is getting into the divider and then out of the divider. But first, as I said, we gotta take a look at the datasheet. And here's a datasheet for it. So it's a really straightforward component. This is now obviously owned by Analog Devices. It's a divide by 8, and if you look at that, this HMC 363G8 is an indium gallium phosphide gas HPT technology. So this is basically the bread and butter of Hittite. I'm not sure if they're making any more of this or not, but it is actually in a glass metal hermetically sealed package because it has to, because it's a gas process, and that is expensive. And it only works between DC to 12 gigahertz. I mean, I can make you a static frequency divider, which is what this is, in like a day in a CMOS or in a silicon germanium process. In a silicon process, okay, maybe its phase noise may not be as good as this, because if you look at this, the additive single sideband phase noise of this component is minus 153 dBc per hertz at 100 kilohertz offset, which is obviously quite good. So it has almost no additive noise whatsoever. It'd be a little bit harder to do that in a CMOS process, but nonetheless, it's going to be quite expensive, and the cost is offset by its performance. Now, if I look at the block diagram inside it, this obviously matches what's on the board. Makes sense. It has a differential input going into an amplifier buffer, into a divide by 8 static divider chain, and then an output driver coming out of out and out bar there, and it's got VCC and internal decoupling caps and so on. So really straightforward, but looking at that board, obviously they're not using it differentially, because the Yig oscillator output coming from the Wilkinson is single-ended, and they don't make a differential anyway, so they have to have terminated the other ends. And in the datasheet there's talk about that you can terminate one side and then terminate the other side, or take it differentially. It will do single-ended differential conversion because of the buffers that are there. So other than that, it's really pretty straightforward. It's got, you know, I think have I ever talked about this before? Some component like this before? I don't remember. But anyway, there's all these performance plots and blah blah blah, the window it works at, and you can check it out. There was something else I wanted to show you. Oh yeah, here you can see the circuit representatives at the input and output, and they're all HPTs. That makes sense. So it's nice that they do this. Hittite was very good at making these type of things, this kind of style, which is very handy. And they know, you know, when a real engineer, a real circuit designer looks at that, they want to see this because it's so intuitive, quickly tell you what's going on. I can see my 50 ohm termination, I can see my output driver, I can see what I'm connected to. Very cool. So I like that. But anyway, so let's go and look at the box of mysteries, see if we have one of these. So I looked around the parts because I remembered working with one of these components just to see if I have one, and I saw this and I got really excited. But this is actually an HMC365. This is a divide by 4 and not a divide by 8. So this not the component there. But anyway, I looked on DigiKey and these are $20 each, the 363. I'm not going to buy one obviously because we haven't tested it. Maybe the one that's there is working. I just got curious to see where I remembered this, and I think I replaced one of these in an Agilent part before. Anyway, so let's go back to it and see if the divider is actually working. Alright, probe is connected, it's configured. Now we can go and measurement. Oh no, Pooch, get out of there! Oh, alright, now we can go ahead and measure. Let's take a look. So first thing first, let's see if the signal is coming out of the Yig oscillator and making it to the divider. Now I have the Yig down there, 5.49 gigahertz. That's what we expect to see going into the divider. So I'm going to go and probe that, and unfortunately I don't know how well you'll be able to hear me, but I'm going to have to describe what I'm doing because I cannot have both of these at the same time being recorded. They're too far apart. So let's see, I'm going to check the signal into the divider, and let me see if I have anything. So this is into the divider. Yeah, oh, there's something there. Let me see here. Scale. Oh yeah, there is something. It looks good. Yeah, it's nice. It's a 5.5 gigahertz. Yeah, this is on a 200, 400. Yeah, it's good signal. It's pretty big. It's got about 450, 500 millivolt peak to peak going in. That's within the range. That's acceptable. And right on the pin, exactly on the pin of the device itself, so that there's absolutely no doubt. Where is it? Right there. Yeah, it's there. Okay, so there is definitely signal going into the divider, so that's not an issue. But the question is there signal coming out of the divider? Now the out of the divider, the signal is DC coupled, so we change that. It's DC coupled, so we should be able to look at it like this just as well. And the output of the divider is... Ooh, that's not good. That was way too high. Actually, this probe only has a linear range from here to here anyway, so it's going to saturate the probe if it's too high. Oh yeah, it's saturating the probe, alright. And there is nothing there. Huh. There is a signal after DC block. I can look at that too. Ah, there's nothing. Nothing's coming out. Stuff's going in, stuff's not coming out. Look at that. So the input is there, 5.5 gigahertz. Output, nothing. It's just stuck high. That's interesting. Could we really have found a problem? I wonder if this is really the problem, that the divider is broken, and that's so if it's not dividing, obviously nothing's going to work. And we know the Yig is definitely there because it's producing the signal, and I did measure it on the unit itself. So let me zoom into the block to show you exactly where I put the probe. So here's a close look at the component, and you can see that our signal is coming in here, and there is a DC block right there as required by the component itself, because the component is DC blocked at the input. And after that I did measure it there, and there was signal, and the output of the divider differential, and you can see the other side is terminated, right? They're not using it. The other side of it, the divided output, is AC coupled into 50 ohm on one side, and on the other side is taken out. And I measured both of these outputs, and they were both stuck high. So it's very much possible that this component is actually dead. And if it's dead, then the loop cannot be closed, and of course the heat would be unlocked. Exciting. Let's go ahead and take this out and see if we can figure out. Now, I have to go and order a part from DigiKey, which means I can't replace it, but at least I can take it off the board, and then we can start our way from there. And check it out, I got the part from DigiKey. And I also wanted to quickly talk about something else. Here I have the Mantis Elite, which is from Vision Engineering. Now, I first used a Mantis style microscope 10 years ago when I was in university, and it absolutely blew my mind. This is a stereo microscope with a specific technology patented by Vision Engineering that gives you a 3D view of the item you're looking at, and by tilting your head left and right and up and down, you can peek around the corner of the component that you're viewing under the microscope. I have shown this to a lot of people, and I can say without exception, anyone who's ever looked through one of these, their first expression is, wow, how is this even possible? It's unlike anything else that you've ever looked through. The quality of the optics is exceptional. There's nothing I can tell you or even show you with a camera, because you're not looking 3D through the camera, to give you the impression of how amazing this instrument actually is. It's one of the best microscopes that I have ever used, and I've used a lot of microscopes over probe stations for a wide range of applications, and I really, really like this. If you have never used it, you can ask them for a demo. Take a look at it. I get no money, no royalties, nothing. This is just my pure opinion, having used this thing and other products from them in the past decade. I cannot recommend it enough. Definitely check it out. You'll see me using it all the time during my repairs. But anyway, so let's go back and put it under the Mantis and do some repair. Alright, here's step number 1, removing of the old component. Now we'll put a new one in. So I went ahead and did the test. It's now a couple of hours later. I showed you that I took out this HMC 363 part and I put the new one in, and it didn't actually solve the problem. And I had to go back and look at the board very carefully and do much more reverse engineering, because it wasn't sufficient. So I'll try and explain to you what's going on so that we can go ahead and continue debugging this. So here is the picture of the board. So we can look at this and figure it out. Now I spent quite a bit of time, as you can see here, from all these different data sheets up here. I went over and looked very carefully at the board and traced some of the stuff out and figured out the architecture of it. Remember, I don't have the schematic, I don't have a block diagram, and to create the schematic for this is just a nightmare. But to get a general idea of how it works should be sufficient to debug it. So as I mentioned before, you can see that here's our EEG oscillator. So we have the output of the EEG oscillator going to this connector. So we know what this connector does, and we know that this connector is a 400 megahertz signal. Now I went ahead and checked this portion of the circuit very carefully, and this portion of the circuit is a 400 megahertz synthesizer, and it works perfectly. It's locked. I verified that. I looked at the signal. It looks good. Now the output of that, so this 400 megahertz signal goes through this part, and this part is a programmable prescaler that divides the signal down to about 85 megahertz or so. So that we have an 85 megahertz signal coming from here that goes into this block, and this block is a phase frequency detector. And this phase frequency detector is functional, but the signal coming into its reference port and the signal coming from the feedback of the PLL are not at the same frequency. And that's obviously a classic sign that the PLL is not locked. It means that there is something else wrong, even though this phase frequency detector is working. I also checked these buffer amplifiers that follow, and they're also okay. So the problem was not really in this section. Now if I continue with the signals, I will discover a few other interesting things. Now the component I replaced was here, and the reason this component wasn't working initially is because the power supply of this is turned on and off depending on the mode the instrument is in. So this is not always on. Now I did verify that when the power supply was on, this component was actually bad. So replacing it was helpful, but it wasn't the only problem. So if I were to continue here, I can see that the signal from the EEG oscillator after the Wilkinson comes through here. These are all amplifiers, these white blocks. And then it follows all the way, eventually it reaches this component here. Now after some digging around and looking around, even though it has no markings on it or anything, I had to trace the signals and look at them and interpret them. It turns out that this is a subharmonic mixer. And this makes matters much more complicated, because it means that the PLL that operates on the EEG oscillator itself is a mixer-based PLL. So it's mixing with another signal, which means that the other signal also needs to be locked. So now we have multiple PLLs nested within each other in order for this whole system to work, making it much more complicated. Then I turn my attention to this portion of the circuit. Now we have a saw oscillator or some kind of an oscillator here, and then we have frequency dividers here. We have a synthesizer IC here, or another phase frequency detector, I should say. It's not a synthesizer IC by itself, it's a phase frequency detector also from Hittite. And I looked at this, and it turns out that this is unlocked. And because it's unlocked, if you look at the output of this, it goes this way through a divider. This is another divider here, and then it goes into this part of the circuit. Now the signal coming from here is used to lock this whole synthesizer again, and then there's a mixer up here. And this mixer mixes the signal from this synthesizer from its own to generate another signal, which then in turn is used over here. So now you can imagine that there's a lot of interdependencies here. And this is a subharmonic mixer which mixes with, I think, the 12th harmonic of the signal that comes over here to generate the down converter signal, which is then fed through here into here. So therefore, in order for this PLL, in order for the EEG oscillator to lock, this needs to lock, this whole section needs to work, this mixer needs to work, this subharmonic mixer needs to work, and the phase frequency detector needs to work. So I went ahead looking around and digging the data sheet for multiple parts, and just to get an idea of the architecture of this, and I started looking at critical points. So I started testing important things like, the phase frequency detector here, this phase frequency detector, I checked various dividers here, I checked this as a counter, I checked that, I checked this phase detector here, I checked this mixer here. These all worked. I checked the amplifiers over here, which do single-ended differential conversion through this balun. I verified all of these that were working. And then I came across this component in the corner here, this one. This is another counter. This is a 5-bit programmable counter, and obviously it's used as a part of a fractional type divider to make this PLL to work. And the signal from this, the output of it, comes back and goes to this phase frequency detector. So when I looked at the output of this signal, it wasn't there. No matter what configuration this chip had, it just simply was not producing a divided clock. And if this divided clock is not there, this phase frequency detector will not be able to lock this saw oscillator. So this will be free running, this signal over here. If this signal is free running, then this entire PLL is not going to work. Then this is not going to work. This mixer is going to be off in frequency, and this subharmonic mixer up here is going to be off in frequency, and then this guy is going to have difference between its reference and its feedback signal, which is exactly what my observation is. So having said all of that, I went ahead and looked at this, and I ordered one, and I got it, and that part is over here. Is another Hittite part. It's an HMC 394, and this is again another gas HPD. It's a programmable 5-bit counter, DC to 2.2 gigahertz, and if I look at the block diagram of it here, you can see it clearly here. And this block diagram has 5 bits, and depending on what bit configuration you put here, it's going to divide by n, and that n number can be determined by looking at, where is it? At this truth table. So when the main board is running, I went ahead and I looked at these bits. These are over here is where those bits are fed in. And I looked at that, and I checked and I made sure that those bits were there, but it still wasn't producing output. So having said this, let's go ahead and replace this and see if we can get it to actually do anything now. Well, having said all that, let's see if replacing this component, the programmable 5-bit counter, will have an influence, given that, at least in the condition that it is right now, it's not producing any signal. So let's give that a try as well. And here we are, the new component has been placed in the instrument, and this is the old one, you can see, and this needs to be replaced with a hot air machine simply because it's soldered at the base, at the bottom of the component as well. So I put the new one in. Now we can go ahead and power the unit on and check the same thing I was talking about before on the picture of the board there, and we can look at the configuration of the bits going into the programmable divider and see if it's producing an output, because it certainly wasn't producing an output before, even though it had the appropriate input. So if it's producing an output, at least we've taken a step forward. and then from there we can go ahead and see if the unit passes the self-test then. So as the instrument is booting, we can go ahead and measure the digital configuration that is present on this 5-bit divider and see if that corresponds to the output and see if there is an output right now. So the power supply going into the unit should be 5 volts, and it is 5 volts, so that looks good. And let me see now, I'm going to measure the bits of the divider from the least significant bit to the most significant bit. So here, least significant bit is a 1, so we have a 1 there, then we have a 0 as the next bit, 1 as the bit after that, another 1 after that, and a 0. So now we can take that and take this into, from binary to decimal and find out what the exact divide ratio is. But I don't even care about it at the moment. I just want to see if it's producing an output, because it wasn't producing an output before. And that will be the first test. If there is something, then we've already taken a step forward. So let me rearrange the camera so we can look at the scope. So let's go ahead and measure the output of the divider now, and I'm going to use the same probe as before. So, and I'm expecting to see something around 100 megahertz based on what we were talking about. And where is the output here? Let me see if we can catch that. We should do a differential measurement. And there you go, check it out. Looks nice. It's well, it's not the greatest square wave looking thing, but indeed there is a frequency of about 100 megahertz. So now this is coming from the divider. Now if I compare this with the signal going into the phase frequency detector, they should be matching now. They should be very similar. Here we go, landing on the other one. And this is the reference coming in, and look at that, you see? This one obviously looks much nicer, it's much more square than the other one, but now they have the same frequency. Now we should be able to run some diagnostic and see what happens. So I'm putting this back together, and I realized I didn't show you the other side of the instrument where the digital board is, and you can see clearly, here's the main hard drive. Over there at the very back is the main motherboard, the main digital motherboard that connects everything together. Here's various options that you can see are occupied. This is the wideband IF, narrowband IF, and this is a digital IF processor portion. You can see even has IQ data correctly going back to the unit, the digital IQ output, which is one of the options. So it's got a lot of different capabilities. Obviously, as I said, this is a pretty heavily configured unit, so it's quite nice that we can hopefully bring it back to life now. I have to turn it on and see if it passes the self-test. And there's a few other processing. I think this is the main processor board. So you can see it's all digital, and the connections from the other side of the board basically just come through as individual connectors. You can see one of them over there, and there's a few down there you probably can't see from your angle. But anyway, just wanted to show you the other side of this as well. And there we go. Let's see if it passes the self-test. Now before I do any actual test, now obviously we want to run the diagnostics again. So let's go back to that menu. So it powered on without the error, so which is already quite promising. And we can go ahead and run the first LO test, which was giving us trouble. And the diagnostic power on self-test now all passes. So that's good. And we can run this test, and I'm going to turn on the verbose so we can see the details of the test as it's generated. I'm going to go ahead and run that. Come back here. So you can see that it reads the board ID. The FPGA test passes, registers passes, and there it is. You see first LO diagnostic ADC test. Now the YIG loop error voltage is okay. The YIG loop is locked. The offset and the course are both locked. And the power supplies are there. Still a little bit low on the 8 volt and a little bit high on the 20 volt. But anyway, not worth basically trying to go dig into that anymore. It's functional and it's fine. Now, most likely the reason that component failed is because on the other side of it are 2 voltage regulators, and that component is receiving a lot of thermal stress all the time. But that's just the design. There's nothing I can do about that. But this should again last for quite some time before a possible failure again. So let's exit the diagnostic there, so we can see if we do some basic test on it to see if it's functional. Now, obviously, just because I fixed the LO, it doesn't mean that the whole system is working. So we need to do some tests to make sure that it is capable to doing all the things like de-modulation. It actually can show the spectrum. It can do real-time analysis and so on. So this is what I'm going to do right now. It takes a bit of time for it to come out of the diagnostic because it puts the unit into a special configuration. And there it is. Now it's preset. Now I'm going to use this board here, which is a little board that's capable of generating spurious tones, good for testing real-time spectrum analyzers. You can also generate modulation. It's a low frequency one, it's around 2.4 gigahertz. So for above 8 gigahertz, which is the up-converted front-end version, I have to put something else. But for now, we can figure this out and see if this generates the kind of signals we want to look at. So we know the frequency center of that board, so we can go ahead, oops, if I can get everything at the same time here, but anyway, it should be good enough. So the center frequency of that board is 2.445312 gigahertz, so we can put our center there. Now if you look over here, you can see that the span is 40 megahertz, but this instrument actually has the option for a 110 megahertz analysis bandwidth. So we should be able to do real-time. If you look here, you see it says real-time right underneath where the mouse pointer is. So it is still doing real-time. Now if I go ahead and change this from 40 megahertz to 110 megahertz, it will still be in real-time as well, which is great. So this has full analysis bandwidth, and it can do DPX on the full 110 megahertz bandwidth. So let's go ahead and enable that. We can go ahead and select the window, and we want to look at the DPX, which is one of the neat things that this can do as a real time, and we can also take a look at the spectrogram. Why not? And let's go and enable that. And we're going to get two other windows. Here's our real-time spectrum analyzer. Here's our waterfall spectrogram, and here's our main spectrum. So let's go ahead and enable the tone. I'm going to turn this guy on, and it should give us a CW, and there it is, nicely, perfectly in the center, exactly as it should be. So it's working. You can see the spectrogram is now updated. Now I can put this into a mode where it generates spurs which are 100 microseconds apart, and they are not very frequent, and see if the DPX can catch them on this unit, and there should be no problem doing that. So I'm going to put it on that, and let's see if we can figure it out. Now check it out. You see that? Every time this pulse comes up, it has no problem catching that pulse. But if you look at the spectrum, if you were only doing regular spectrum analysis, you would miss them. You can see that so far we see them all the time, but not a single one has shown up here yet. So this is the advantage of the DPX. So it's working quite nicely. Very happy with that. So let me close this waterfall here so we can see side by side the difference between a real-time spectrum analyzer and a spectrum analyzer that can do digital modulation analysis, but it does not have real time. So this is quite nice that that capability is there. Now we can go ahead and generate some QPSK signals, and we should be able to see that a nice spectrum for a QPSK appearing. Very good. And now I should be able to demodulate that if that's also working. I can go to the demodulation, constellation, and go OK. And there it is. You can see the constellation is there. I've already set it up before with the numbers in advance, so you can see that it has no problem demodulating our QPSK signal. I can go ahead and remove the traces and only look at the points, and there it is. You can see that it's working perfectly. It has a full 110 megahertz analysis bandwidth. Real-time spectrum analyzer is working. The tones are the correct amplitude, so it seems to be fully functional. The only other test that I would like to do on it is the test where we would use a source that goes above 8 gigahertz, because right now we are never engaging the first converter, and I want to make sure the first converter is also working. So we need a source above that, and I'm just going to put a CW source on it so we can check it out. And to test the higher frequencies, I'm just simply going to use this synthesizer module. This is a 9.3 gigahertz synthesizer. It generates a single tone. It's used for high purity tones for other applications, but for our purposes just a CW tone should be good enough. So right now it's turned off. I've centered the instrument at 9.3 gigahertz, and there's nothing there right now. If I go ahead and power on the module, and there it is, you can see that we can measure a 9.292575 gigahertz signal, a 10 dBm tone coming into the unit perfectly fine without any problems. And one other thing I wanted to show you here is that the record length is 2.593 microseconds. So at 110 megahertz analysis bandwidth, it records 2.953 microseconds of data in its memory and analyzes it, which is quite nice. So it's a really capable instrument. I mean, when this came out, it was basically one of the state of the art. Now there's a B version of this instrument also available. Now, one of the things I didn't show you, which I thought perhaps you might have wondered about, if I go under diagnostic again, if you remember, the signal path was also failing before. Now I told you that it's most likely because of the LO, so I can run a test on the signal path separately. I can run that test, and you can see it's clicking and going through some internal tests, and this is where it reroutes perhaps the CW tone generated from the LO board and uses that, and you can see that it passed no problem. If I go over here all the tests have passed. So this was the one that was failing, the 200 megahertz CW cal source. Now it's there. So it is, as far as I'm concerned, a fully functional unit, and it passes all my tests that I did also off camera. So I would say that's a successful repair. Now this was a pretty risky one. I don't necessarily recommend that you would go and do something like this, because there is no block diagram or schematic at all available for this. So there's always a chance that the repair will be non-successful, and I did spend several hours looking very carefully at it and trying to figure out what's going on. So it is pretty time consuming, but I'm pretty happy that it's successful. So if you like it, let me know in the comment section if you have any questions. We can discuss it, and check out the Patreon page. I added some goals to it which should be interesting, and yeah, we'll go from there. Until see you next time.